my name is Nur Aura Ishira Vidusakimi and my matrix number 229594. I will explain about how to use the equipment and all the data that we need to record for cooling tower experiment. First, we need to turn on pump, turn on fan, and we need to adjust the heater to 1. Next, we need to fill the tank until it reaches 3 liters. So we need to adjust water flow until the value becomes 20 liters per hour. After that, there is a few parameters that we need to record. First is air inlet and outlet temperature, relative humidity for inlet and outlet, supply tank temperature, water inlet and outlet temperature, water flow rate, and differential pressure. Lastly is makeup water quantity. After finishing all the data, we need to switch off pump, fan, and adjust heater back to 0. That's all for how to use the equipment for Pelton turbine. Thank you.
So what is the main findings of this experiment? So there's 3 main findings. The first one is cooling range versus heat load. Our first major finding relates to the system cooling range, which is the difference between the water inlet temperature T4 and the water outlet temperature T5. During the experiment, we applied different heater load at 0.0 kW, 1.0 kW and 1.5 kW. We observed that the cooling range increased as the heater load increased. We were also able to compare how different combination of water and air flow rate impact this cooling performance. So the second finding is wet bulb approach. Another key performance measure we evaluate is the approach. This tells us about the effectiveness of the cooling process by looking at how close our outlet water temperature, which is T5, is to the air inlet condition, specifically T1 and M1. We analyze this relationship to understand the theoretical limits of cooling in our setup. So the third and last finding is mass and energy balance. We also perform a mass and energy balance on the system. For the mass balance, we verify whether the quantity of makeup water we add over the course of the experiment successfully match the humidity increase we saw between the inlet air M1 and the outlet air M2. For the energy balance, we check if the power applied by the heater match the observed cooling effect and energy transfer in the system.
So what we can conclude from our wet cooling tower experiment? To conclude our findings from the wet cooling tower experiment, we evaluated the system's cooling performance by analyzing the cooling range, which is observed temperature difference between the water inlet and the water outlet. And we also examined the approach to the air inlet conditions, specifically observing how close the outlet's water temperature gets to the initial air conditions. And in the end, based on our mass and energy balance calculation, we can conclude whether the makeup water quantity match the humidity increase at the air outlet, and if the applied heater power accurately corresponded to the observed cooling effect.
This experiment demonstrates how engineering systems manage heat in real-world applications. From our results, we observe that as heat load increases, the cooling range also increases. This reflects how systems like power plants and HVAC units remove more heat under higher thermal demand to maintain safe and stable operation. We also found that airflow and water flow significantly affect performance, where higher airflow improves heat transfer. Engineers use this principle to optimize systems by adjusting fan speed and flow rates to improve efficiency and reduce energy consumption. This relates directly to engineering design in industries such as power generation and HVAC, where efficiency and safety are critical. Another key concept is wet bulb temperature, which represents the limit of cooling and is used as a benchmark for performance evaluation. Overall, this experiment applies heat transfer, fluid flow, and system optimization principles.
Cooling tower
experience to show how heat can be removed from the water by letting the air and water interact. In real life, this process is very important in places like power plants, factories, and large buildings. For example, in power plants, cooling towers help to remove the waste heat to the system that can keep running safely and efficiently. In industries, they prevent machines and equipment from the overheating during the continuous operation. Even in the big buildings, cooling towers are part of the air conditioning systems that help to maintain the comfortable indoor temperatures. From the experiments, it's become clear that air flow rate and water flow rate have a big impact on how effective the cooling process is. This is why engineers pay close attention to these factors when designing the air conditioner or any cooling system. Overall, cooling towers are important because they help to manage heat efficiently, save energy, and support more sustainable industrial operations. That's all from me.